Hey guys, I have a short video here for you on sigma notation. Alright, so we've all seen sigmas for, Greek life and whatnot, but for us, what sigma is going to mean is sum. Okay, so if we have this notation here, maybe we see k equals 1 to 6 of f of k. So you have some function f, and what this means is this is your lower bound, where you start, and then this is your upper bound. And so you're just going to iterate this process. So you plug in 1, you get f of 1, and we only go up by a step of 1 each time. So it's not like you have to worry about decimals. It's plug in 1, plug in k equals 2, so we would get f of 2, plug in k equals 3, plug in k equals 4, plug in 5, and then this top tells us when to stop. So we go exactly until f of 6. Okay, so that's what this would be equal to. So let's see an example where I actually give you a function f. So let's do a real simple one. Let's just look at when f of k is k itself. So if I write here, let's just sum from 1 to 5 this time, say. And we would put k here on the inside because that's my function. And so this says, okay, I plug in k equals 1. All right, now I add k equals 2 is my next step. 2. K equals 3. And I add until I hit that top bound of 5. And then I can actually just add this up, right? So it's 3, 6, 10, and we get 15 as our answer. So let's do one more with maybe a slightly more complicated function. So what if we had our function is 2k plus 3, and I want k equals 1 to 3 of f of k here. So again, step 1, well in this case, f of 1 is what? It's going to be 2 times 1 plus 3, that's my first term, plus, now I plug in k equals 2, 2 times 2 plus 3, and then lastly, 2 times 3 plus 3. And then we can just add these up. So this is 5, then we get 7, and then we get 9. And so when we add these up, we get 21. Okay? All right, and so for your first little class prep exercise, go ahead and compute this sum here. So k equals 1 to 5 of 3k minus 2. Okay, so why am I introducing sums? Why am I talking about sigma notation at all? Well, the relevant sums here are what you learned for your last project, which are Riemann sums. Right, so the idea behind Riemann sums is maybe we care about this definite integral, and maybe it's a weird shape, right? We have something that looks like this from A to B, and so we're talking about this area in here, and this is our f, and we're like, that's kind of hard. I don't really know what the area of that shape is, and so what we do, we approximate it with rectangles, right? And the whole point here is that as you make your rectangles thinner and thinner, this approximation gets closer and closer to the actual area, right? And then a Riemann sum is just the sum of the areas of our rectangles. So that's where the sum comes into play. Okay, so let's try to walk through an example here. Okay, so for our example, we're going to look at the integral from 0 to 2 of x squared dx. So I've drawn x squared over here from 0 to 2. I want to try it with two rectangles using right endpoints. And again, we actually don't necessarily care about having different widths, but we're all lazy humans. You should use the same width. So in this case, if I have two rectangles and my interval is length 2, they should both be width 1. So I'll write that down, right? So these are width 1. And so if I want area, right, so I'll put an approximate here. This should be just the sum of two rectangles. And if I'm using right endpoints, right, that means I'm looking at the right point of my first interval from 0 to 1, make that the height, and then again, right endpoint here at the second interval from 1 to 2 and drop that down. And so this red area is my approximation. This is clearly an overestimate in this case. And so if I call this area A1 and this A2, then this is approximately just this A1 plus A2. But another way, if we wanted to use, sums using sigma notation, something that maybe could generalize to more than 2 rectangles, if we wanted to do, say, in rectangles, because eventually we want to make them thinner and thinner, then maybe we want to get a general formula. So what is my area? It's width times height, right? And in this case, we are going to have width 1, so it's actually just straight up equal to our height every time. But what is our height? So basically, what happens here is we're plugging something into x squared each time, right? That's how we're getting our height. But what are we plugging in? So we have 2 different areas, so I should be doing like k equals 1 and k equals 2 for my different areas. And then in this case, I'm literally plugging in 1 and I'm plugging in 2 because my width is 1. And so this is actually just straight up f of k. I'm plugging in k to x squared, and so I get k equals 1 to 2 of k squared, and then we can just see this is 1 squared plus 2 squared, which is 5. Okay? So now let's see how to do this, again, more focusing on what I've written in blue, for 4 rectangles instead of 2 when the width isn't so simple at 1. So in this case, what's our width? Well, we have 4 rectangles. We're still going from 0 to 2, so it should be width 0.5. And so our right endpoints would be at 0.5, 1, 1.5, and 2. And so each area, so if I want to start thinking about this in terms of a sum, now I have 4 rectangles, so it should be k equals 1 up to 4. I'm adding up 4 different areas of width, which is 0.5 or 1/2, times my height, which is f of, well, in this case, it's not just k, right? We're not plugging in 1, 2, 3, and 4. We're plugging in k over 2, right? 1 divided by 2, 2 divided by 2, 3 divided by 2, 4 divided by 2. And then now we can just kind of simplify here, right? So this is still just 1/2 times, well, this is k over 2 squared. So this is k squared over 4, otherwise known as k squared over 8 over here. Well, now I can add these up really easily, right? So I would just plug in 1 plus plug in 2, 4/8, plug in 3, 9/8, plug in 4, 16/8, and I end up with 16, 25, 29, 30/8, or 3.75. Okay, and this is much less of an overestimate because I've taken away a whole bunch of error by giving more rectangles. Okay, and for your second exercise to close up here, I want you to do basically what I just did. Compute the Riemann sum for x squared, again from 0 to 2, using 4 rectangles, but instead of right endpoints, I want you to use left endpoints. So your width should still be 0.5, but now your heights should be different. And see if you can, while doing this problem, use sigma notation. Okay? Thank you for watching.